really the stages or the steps to take when you are solving these questions. So today we'll just practically be looking at how you can be able to make, or rather how you can be able to solve these questions. So basically that's what we'll be looking. Since we discussed how to go about, so I will now be able to solve. So what's the question really asking of us? So what the question is asking of us is, you've got okay, so you've got a certain reaction which is occurring, and then what they've done is they want a certain, okay, so they want copper to be plated on something. So plating of a metal is simply putting that metal onto something, right? And of course in this case we'll be putting it on the chlorine, on the copper electrode. So plating means depositing the neutral metal on the electrode by reducing the metal ions in solution. So then one thing that is important here is, for remember, the solution contains copper 2 ions, and for this to be reduced they need how many electrons? For each to be reduced they need how many electrons? 2. Now, why am I stressing on this? I'm stressing on this because this is a very important point. An important point in the sense that when we calculate the number of the moles of electrons, as we would do, we will use that equation to then determine, okay, I hope you are following me, to then determine um, how many electrons or how many ions of copper have actually been converted. So what have we been told? So we are passing a current of 10 amps, okay? So a current of 10 amps is being passed. So we've got a current of 10 amps. Okay, so we've got a current of 10 amps. So we know what is 10 amps. So 10 amps is the same as 10 coulomb of charge per second. Since 1 amps or 1 ampere is what? Is 1 charge, or is 1 coulomb of charge per second. So 10 amps is 10 coulomb of charge per second. So then what this means is that, yeah, so they were passing this current uh, for 30 minutes. Okay, so they were passing this current for what? For 30 minutes. Now, what is important and interesting here is that we want now to determine, to say, if per second they were passing how many coulombs? 10 coulombs of charge. How many charges or coulombs of charge were actually passed in what? In 30 minutes. So to do that, we first have to convert that 30 minutes to seconds. So how we are going to do is, we are going to say coulombs of charge. So we discussed these steps last week. So today we are just solving. Remember, the aim is to find the mass of copper that will be electroplated when this is done. So the coulombs of charge, we say it's 10 coulombs per second, coulombs of charge per second, then times what? 30 minutes. Now you know we don't use minutes, so we convert the minutes. Since we want to go to seconds, so seconds will go on top, then minute goes down, so that the minute cancels that, and then we are going to have our value. Okay, so okay, and of course the second there cancels the second, that's over. And then once we do that, we are going to have our charge, which is that. So you see, that's the beauty of using units, because the units will guide you. If you've got something wrong, the units will guide you. So now what does this tell us? So this tells us that in 30 minutes, this was the amount of charge which was actually passed through this solution. Now, what do we do with this solution? Since we know the amount of charge, or the column of charge which was passed, we have got an important point, which is a what? Which is the Faraday's constant. What does Faraday constant tells us? So Faraday constant tells us that one mole of electron, that's one mole of electrons. So one mole of electrons is what? Is 96,485 what? Coulombs. So if we have this amount of coulombs, how many moles of electrons do we have? I hope we've gotten that analysis, right? So then what you're going to do is, you're saying, so you cross multiply here, and you're saying 96,485 columns of charge. Then you say 1.80, then times 10 power 4, then one more of electrons, huh? So what do? You divide 96,485 coulombs over, okay, so the same thing on this side. So the coulombs go, they cancel, right? So what you're remaining? Now you're remaining with the number of moles of the electrons, which were what? Which were actually involved in this. Okay, so you have that moles of what? Electrons. So let's write it properly. Moles of electrons. Okay, so these are the number of moles of electrons. Now, once we've gotten the number of electrons, remember I said something about how important this reaction was. You know how important this reaction is? It's because it tells us to say, if we've got this number of electrons that are flowing, how many electrons are required to convert copper to ion, to convert one copper to ion to copper atom? You need 2 electrons. So if we need 2 electrons, what that tells us is the moles of copper atoms which are going to produce from these electrons is going to be half. Why is it going to be half? It's because to convert one uh one mole of copper to ions, you need how many electrons? 2 electrons, isn't it? So what this basically tells us is that you you need so these electrons, they will supply half this number of electrons of copper uh, to ions to convert them to what? To copper atom. So what we are going, and we are using the ratio there, right? Since each copper 2 ion requires 2 electrons to become a copper atom. So meaning the number of electrons that we have there, each mole of electrons produces half a mole of copper. So what we are going to do is we are going to say for the, so we are going to say the moles which we have here And then, so the ratio we are saying it's one for 1 mole of copper, it's what? It's 2 moles of what? 2 moles of electrons, huh? Which I was explaining. So what we are going to have is the moles of electrons cancel, and then what you are going to have is half. Huh? So half of that, so you have that, right? So those were the moles of copper, which can actually, which were actually converted from copper to ions to what? To copper atom. They from the electrons which were passed through the solution. So once we've done that, then we now use our mole concept to find the mass of the copper based on the what? Based on the number of moles. How do we do that? We say mass is equals to number of moles. So number of moles times what? Times the molar mass, isn't it? Molar mass, atomic mass, those things. So the number of moles we have, and then the atomic mass. Of course, per mole of copper. Since it's grams per mole, so what happens? The moles cancel, and what you are going to remain with is 5.94 grams of what? Of copper. So means that in this time where the current was being passed 10 amps per second, or rather, no, not 10 amps per second, 10 amps, of which we know that 10 amps is equal to 10 coulombs of charge per second, and was being passed in 30 minutes. So from here, we've been able to calculate the amount of copper. So that was the amount of copper that was plated on the electrodes. So these are some of the important chemical reactions which occur in chemical plants. So then now let's now look at uh, where now we've been given the mass, we've been given the current, and then now we have to calculate the time in which that was achieved. So let's look at an example so that once we do this, then we are practically done with this topic. So that example there, yeah, so electroplating, these examples are really liked, so it's good that you get your hands around it. So example what? Example 18.11. How long must a current of 5 ampere be applied to a solution of silver ions to produce 10.5 grams silver metal? So if you really think of it, it's just almost like just working backwards from what we had discussed, isn't it? So what we're going to do is we've been given the mass. So what can we do with the mass? Well, what we can do with the mass is to calculate the number of moles of silver which have actually been produced. And once we know the number of moles which have been produced, then what we can do is be able to convert and relate those number of moles to the coulombs of charge. using the Faraday's constant, isn't it? Because Faraday's constant gives us the charge per mole, and then we do justice like that. So let's then see how we are going to answer this. So then what we are looking at is, so we've produced 10.5 silver metal. So we've produced 10.5 grams of silver, isn't it? Now, what is happening now is that we are then trying to find how long must a current of 5 ampere be applied to a solution. Be applied to a solution of what? Of silver ions to produce that mass. So then what you are doing is you want to find how many moles of this same ion, of this same silver was produced. So it's going to be number of moles, it's equal to mass over molar mass or atomic mass, depending on what you're looking at. So the mass in grams, 10.5 grams over, so here you're going to have 107.868 grams per mole. So per mole, of course, per mole of silver. So of course per mole of silver. So the grams cancel, then you remain with the number of moles. Okay. So number of moles of what? Of silver. So now what do you do now with this number of moles? So now what you do at this point is you want to write the reduction equation for silver, because I've said it contains silver ions like that. So it's just each is just going to need one more of electron to form a solid from an ion. So we know the number of moles that are involved. So these moles of silver that we found, since the ratio between the silver ions and the electrons is 1 to 1, it basically means that even the moles of electrons that are going to be required to do this is going to be what? The same. So it's going to be 9.73 times 10 to power negative 2 of what? Of electrons. I hope everyone is clear on that part. So after you've done that, then you now go back to the Faraday's constant. So remember, Faraday's constant says one more of electron produces what? Produces 96,485 coulombs of charge. So now I've got this number of electrons. So what charge will they produce? What coulomb of charge will they produce? Okay, so we have that equation. So once you do that, you are then going to say, so X more of electron, then you're going to have 6,485 coulombs. So that's coulombs. Then 9.73 times 10 to power negative 2 more electron over 1 more electron over 1 more electron. Do I have that? So we remain with charge. Okay. Okay. So we have that. So now from here we are now remaining with the time now. So what have we been told so far? So what we've been told is the amount of current that's being passed is what? Uh, the amount of current being passed is 5 coulomb per second. And so we know that time, so times, anyway, let me write this in a way that would be easier for everyone to appreciate. So we are saying 5 seconds, so 5 coulombs is being produced in 1 second, because that's what 5 coulombs per second means, isn't it? It means that 5 coulombs are being produced 1 second. Then if we then have 939 times that coulombs, let's find the number of seconds. Okay, so that's what we are looking at. So we say 5 coulombs, then x, then 1 second times okay, then you have 5 coulomb. So you cancel that, you cancel that. That's going to be second, right? Of course, you can use the necessary conversions to convert this to minutes, because of course minutes would be easier for somebody doing an experiment, which would be 31.3 minutes. Of course, we know the conversion factors, isn't it? Okay, so 31.3 minutes. So that's basically how you would go about these particular questions. And so, having done that, we now look at the last part, which is this. So, even though there may be mixtures, okay, so even though a solution may have mixtures, but you can be able to predict and say, for this particular reaction, if you've got a mixture of ions, you can actually be able to predict and say, okay, the order in which uh, the reactions are going to take place is going to be this and that. So, for instance, there it says electrolysis of mixtures of ions Suppose a solution in an electrolytic cell contains ions copper 2, silver ion and zinc ion. If the voltage is initially very low and is gradually turned up, in which order will the metals be plated onto the cathode? So, simply put, they are just asking in what order will which metal will be reduced first? That's the question. So you have to go and look at the table there, but they've given us already their reduction potential. So remember, the more positive the value is, the standard potential is, the easier it is, or the greater the tendency for the reaction to proceed in that direction, the more positive the E value, isn't it? So meaning from these E values, we would expect the reduction of iron, pardon me, the reduction of silver to occur the quickest, isn't it? Because the standard reduction potential for silver is the largest of these three, or is the most positive of these three. Then followed by, of course, for copper, then zinc being the last one. That's why zinc is usually oxidized. That's why it's all used to protect the what? The rusting of other metals. So that's something we discussed when we were talking about corrosion. So this means that silver will plate out first as the potential is increased, followed by copper and finally zinc. So now the last exercise, then we are pretty much done. So let's look at it there. Okay, let's look at it like that. So then we are looking at this particular question, and then okay, so an acidic solution contains the ions, so there is that one, and that one, using the standard reduction potentials listed in table 18.1. So it's that table that we looked at some time back. Give the order of oxidizing ability. So here they've talked about oxidizing ability. Huh? So what is something that oxidizes? Remember, something that oxidizes is something that is reduced, isn't it? So the easier something is reduced, the better it is an oxidizing agent. Because for it to be reduced easily, it means that it's making it easy for the other substance to lose electrons. So then it's an oxidizing agent, right? Okay. So using the E values listed in table 18.1, give the order of oxidizing ability of these species. Okay, of these species, and predict which one will be reduced at the cathode of an electrolytic cell at the lowest voltage. So basically what they are saying is which one is easily reduced and which one will be reduced at the cathode at the lowest voltage. So something that can be reduced at the lowest voltage in an electrolytic cell, we are basically saying this is something which is easily what? Easily reduced. Which one is easily reduced? You look at the what? The standard cell potential. Okay? Which direction is favored? So we look at those half reactions and we see that the oxidizing ability is simply the what? How easily something can be reduced. Because if something can be easily reduced, it means that it's a good oxidizing agent. Okay, so we see there we've got the first one. Of course, the first one can easily be reduced looking at its standard reduction potential. Then followed by the second reaction, then the ion reaction being the last one. So the order is going to be oxidizing agent, so the first one, the second one, then the ion, then Also, the one which will be reduced at the lowest voltage is the one that is easily reduced, okay? Or the one that has got the highest or the most positive. So we say the most positive. Um, so we say the most positive standard reduction potential. So basically, that's pretty much how we go about these things. So uh, the rest of the things are just trying to talk about the innovations which are being made, but however, the things which you have to know, they are the things that we've discussed, the things which are important. So remember, what has now remained is for you to revise, for you to revise, for you to revise, try out questions, try out examples. That's what has remained. So yeah, the topic is it's not really hard. Yeah, because that's all about electrochemistry that you will need to know. That you will need to know. That you will need to know. So that's about it. So now we are talking energy now. So the nature of energy. So we'll leave it there. So the nature of energy. So really, when we talk about energy, it's a concept, of course, which it's very familiar to us, but quite tricky to define. However, energy is the capacity to do work or produce heat. So anyone, anything that can produce work, that can do work rather, that has got the capacity to do work or produce heat, that thing has got energy. And one of the most important characteristics of energy is that it is conserved. So what does this tell us? So this simply tells us that energy can be converted from one form to another, but can neither be created nor destroyed. So what this basically tells us is that whatever form of energy which you are going to have or which you are going to see, it's not created. Okay? It's not created. Rather, what's happening is it's simply created from what? From another form. You can talk about the bulb, the electric bulb. It's simply been produced from what? The light has come from what? From electrical energy. So energy is never created, is neither created nor destroyed, but can be converted from one form to another. So you see on the top left, there are those drawings there. And I'm sure you may remember from the questions that we did in physics on work, energy, and power, where we are discussing how gravitational potential energy and kinetic energy interact. So what's happening here? Let's go for the first part, for the first one, A, for the initial part. So you see that the ball A actually has higher potential energy than ball B. And then you will realize that because this is what's happening when it falls, okay? When it falls from where it was held in place, it hits on ball B, and ball B then gets some energy to then move and rise up to where what? To where it was. And after, so that's after A has rolled down the hill, the potential energy lost by A has been converted to random motions of the components of the hill, frictional heating, and to increase, okay, the potential energy of B. So that's why you are seeing the B there has been raised. So it has gained what? It has gained potential energy. And why this has not been raised to the same height as A was, it's because of the frictional forces and the frictional heating. Okay, so of course that's why we never want friction, because friction steals the important energy which we could have made use of. But of course, it's something that time and again we have to deal with. Okay, so that's about it. So temperature is a property that reflects the random motions of the particles in a particular substance. So the temperature of something is just simply telling you to say, oh, okay, it just reflects. Okay, so maybe the particles in this substance, the random motions are most likely to be this, and that. So basically, that's temperature. Whereas heat on the other hand, rather, involves the transfer of energy between two objects due to a temperature difference. So what this basically means is that heat is the transfer of what? Is the transfer of energy between what? Between two objects due to a temperature difference. So what this entails is that when heat is transferred because of differences in what? In the temperatures of those objects, then that's heat, right? So that's something that's important to take note of. Then you may remember that in chemistry, or rather physics, we discussed work, okay? And so we said work is defined as force acting over a distance. And this is something that we discussed in physics, but you may be wondering why these definitions are coming up, because when we come to talk about chemical energy, we always want the chemical reactions to do something for us. We've talked about the lead batteries, we've talked about different kinds of things, right? So the main thing is we want to know the amount of work that these chemical changes are capable of doing for us, because that's the main purpose why we are actually allowing a battery for, the chemical reaction that is happening in the battery to occur, because we want something to happen, or we want the reaction to do something for us. Then there's something about the pathway. So you see that in the examples where I gave about the ball, we talked about where friction, if friction was there, we see that the distance, or the gravitational potential energy that the ball B would gain would be lower as compared if there wasn't any friction. So again, the pathway is very important. That's why you may have heard that sometimes to increase efficiency for certain bulbs, they have to change the what? That lighting thing. Okay? Because their key aim is to what? Their key aim is to ensure that resistance is reduced, and heat is not lost, energy is not lost, and in that way, the bulb or whatever equipment that you are looking at is going to have a very, very high efficiency. Okay, so that's an important point to take note of. So now, here we've been talking broadly about these particular things. Now we are going to narrow our narrative to now talk about chemical reactions, and there is no better place to start from than the combustion of methane. You may remember in your organic chemistry grade 12 that you used to talk about the reactions of alkanes. You talked about combustion. So combustion is simply something burning in air, okay? Of course, oxygen being the key thing. So what happens is that carbon in the methane, or carbon tetrahydride, as you can call it, uh, the carbon in the carbon tetrahydride is going it's going to be combusted, or it's going to be oxidized to form carbon dioxide, then hydrogen to form water, and energy is going to come out in form of what? In terms of heat. Now this is very interesting, because this reaction that we are seeing is going to form the basis of our thermochemistry, and it's from this that we are going to build really how we'll be looking at our thermochemistry. So when we're dealing with thermochemistry, we always divide the everything that's happening into the system and the surroundings. So, when we say the system is the part of the universe on which we wish to focus our attention. Let's say we say we are focusing on this reaction that we have of the combustion of methane. That becomes our system, and then everything else in the universe becomes the surroundings. So in this case, we would say the reactants and the products of the reaction are the system, and the surroundings would be the reaction container, the room, and anything else other than the reactants and the products. Now, of course, this now brings us to the two kinds of reactions that we have. So, well, of course, with regards to heat or with regards to energy. So, when a reaction results in the production or the evolution of heat, we call that an exothermic reaction. That is, energy flows out of the system. So, take note of the flowing out of the system because that's going to have consequences on the signs that we use for these reactions. And then endothermic, these are reactions that absorb energy from the surroundings. So that's something that's important to take note of. So now remember, but where does this heat that is produced in an exothermic reaction come from? So the key thing is that there's a difference in potential energies between the products and the reactants. And so remember then which has got the lower potential energy, the reactants or the products. So we know that total energy is conserved and that energy flows from the system into the surroundings in an exothermic reaction. This means that the energy gained by the surroundings must be equal to the energy lost by the system. Okay? So now this is very, very important. So in an exothermic reaction, in any exothermic reaction for that matter, some of the potential energy stored in the chemical bonds is being converted to thermal energy, random kinetic energy via heat. So basically here we're just saying it's out of the, remember that time when we were looking up, we were talking about the enthalpy changes, right? Anyway, but we'll discuss them in more detail in this topic. But we're just basically saying at how the bonds were being formed, the bonds were being broken, were being formed and broken, and then overall you would realize that the reactants had so much energy as compared to the products. And so because of that, because the system has, or rather there has to be a balance between the amount of energy that has been lost from the product, from the reactants rather, and sorry, the amount of energy that has been lost by the system has to be equal to that gained by the surroundings. So that's something important to take note of. So so these pictures are just showing what happens in an exothermic reaction, and you see for that energy diagram, you see that for an exothermic reaction, the reactants are at a higher potential energy than the product. And why is it so? It's because the reactants have what? They've lost sorry, the the reactants have lost energy. So the products are what? Are at a lower energy level. Okay? So that's about an exothermic reaction. Now we go to talk about an endothermic reaction. The opposite is true. You see, the reactants are at a lower energy level, but then as the reaction is occurring, the reaction gains energy, gains heat from the surroundings. And what do we see? We see that the products now have a higher potential energy. So this potential energy basically means the capability, the capacity for 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 them to work on something. Okay, so that's something to take note of. So in an exothermic process, the bonds in the products are stronger on average than those of the reactants. That is, more energy is released by forming the new bonds in the products than is consumed to break bonds in the reactants. So that's how the extra energy is produced from what? From an exothermic reaction. For an endothermic reaction, the situation is reversed. Okay, and this is because the energy that flows into the system as heat is used to increase the potential energy of the system. And so, like I said earlier on, the products are going to have higher potential energy, which translates to weaker bonds on average than the reactants. So this now brings us to thermodynamics. What is thermodynamics? So thermodynamics is the study of energy and its interconversions. So how is this energy moving about? How is this energy uh, being transferred? How is this energy changing? So that's something that's very, very important to take note of. So the law of conservation of energy is often called the first law of thermodynamics and is stated as follows: the energy of the universe is constant. Why? Because energy just keeps changing forms. Neither is created, neither is destroyed. It just keeps changing form. From the sun, it comes down, it's used up, again it goes up in some form, just like that, right? So that's about it. So now you remember me uh, explaining and talking about heat and energy. Oh, sorry, talking about heat and wake. So now, here I'm now going to explain more on what those terms mean, and then we can be able to look at examples, and then we can proceed from there. So the internal energy, the internal energy E of a system can be defined most precisely as the sum of the kinetic and potential energies of all the particles in the system. The internal energy of a system can be changed by by a flow of work, heat, or both. So what they are basically saying is that a system, let's talk about that reaction that we had, of the combustion of methane. It's got certain amount of internal energy, which is as a result of the kinetic and potential energies of all the particles, the reactants, products. So it's got a certain amount of energy, but this energy can be changed by uh, whether the system is doing work or it's actually losing energy in form of heat, or both. For instance, let's say for things like a car engine, it's doing work, but it heats up. So the internal energy of the battery or the engine, it's there, but it's being changed because it's doing work. The engine is doing work and producing heat or something. Yeah, doing both, right? So that's the equation that we have. So the change in internal energy is equal to plus what? Plus heat is equals to heat plus work. Now, there are things that we have to understand here is that whenever we are looking at thermodynamic quantities, we always look at two parts. First of all is the number. So the number is the magnitude of the change. So by magnitude of the change, we are saying by the amount. Okay, so the amount of the what? Of the quantities of the weight, the heat. And then the other thing is the sign. The sign indicates the direction of the flow. And remember, in chemistry, we always look at it from the system's point of view. So what this means that if a quantity of energy flows into the system through heat, which is an endothermic process, then Q, it's going to be plus X. So X can be any magnitude, but the sign is going to be positive. Why? The system has gained energy. So it's a plus to the system. So the positive sign indicates that the system's energy is what? Is increasing. But if energy flows out of the system via an exothermic process, then our Q is what? Is going to be minus X, where the negative sign is saying the system's energy has decreased. So how you can think of this is you are adding this, right? So the system, let's say the system has got a certain amount of energy, then you say plus what? Plus X. If you say plus X, the mean, okay, let's say, yeah, so plus X, so the plus, meaning the system is gaining energy, plus X, oh, so X is just any magnitude, right? So meaning that the energy value of the system is what? Is increasing. Whereas on the exothermic, the opposite is true, right? Like I've explained. Then, as we conclude, because of time, then now we can now talk about work. So remember, we are always looking at these things from the perspective of the system. So if a system does work on the surroundings, what does it cost to do work? For you to do work, it costs energy. When you are told to do something, when you are told to clean something, you don't finish cleaning and you are feeling energetic now, do you? No. Rather, what happens is when you are done cleaning, you feel tired. Why do you feel tired? Because energy has flown out of you. Okay? So that's the thing. If a system does work on the surroundings, energy flows on the system. Therefore, the work is taken as negative. Then, if the surroundings do work on the system, whereas energy flows into the system, then the work is positive. Therefore, we define work from the system's point of view to be consistent for all thermodynamic quantities. That is, in this conversion, the signs of both Q and W, which is heat and work, reflect what happens to the system. Thus, we use change in internal energy is equals to Q plus W. But of course, so in this text, in chemistry, we always take the system's point of view, but there are other like engineers, they've got their own way of thinking. So for them, they'll think, you know what, because they are developing something or they are developing a machine to do this, so they usually look at work from the surroundings point of view. So for them, when work flows out of the system, it's treated as positive because the energy of the surroundings has increased, therefore the system is fulfilling its duties. But remember, for chemistry, it's what I explained a short while ago. So you see, if the change in energy, you see that the change in energy is less than zero. So less than zero meaning you've lost energy. Okay, so if you're getting a negative, they mean that you've lost energy, meaning it's exothermic. If your change in internal energy is positive, meaning you've increased your internal energy, so meaning that the reaction is what? Is endothermic. So tomorrow we'll look at these examples and then we would have kickstarted our what? Would have kickstarted our thermochemistry journey. So the convention in this text is to take the system's point of view where Q minus X denotes an exothermic process and Q plus X denotes an endothermic one. So that's pretty much about those particular